Morning, everyone. So yesterday we had a look at hydrolysis. Essentially, we mainly focused on salts, especially soluble ones. They would get dissociated by water. Salts have no business being acid or base, but we found that depending on the cation and anions that actually formed, if they were not spectators, they could actually hydrolyze. They could actually react with water to reproduce a little bit of H plus or hydroxide. We're going to see that a little bit later on again in this lesson here. I did want to practice with you a buffer question from 2 days ago. This one here, I'm just going to pull from your practice question. This one is question number 4. I want to know here how many grams of sodium ethanoate, so sodium acetate, need to be added to 1 liter of 0.100 molar acetic acid, CH3COH, to create a buffer. So a buffer is something that has appreciable amounts of conjugates with a pH of 5.00. Okay? So we know for our buffer system, at the end of the day, I know I want it to be CH3COH. This is in equilibrium, right? It has to be something that's weak. As a weak acid by itself, this one here is not very good at actually producing conjugates. The Ka is heavily reactants favored. So not a lot of H plus, not a lot of acetate. How they're making the buffer here is they're just artificially just beefing up the acetate by adding in sodium acetate. So the question is, how many grams of this acetate should I add so that I have enough of the conjugate amounts and now the pH is actually a 5? Right? First thing I would look at here is, I notice that this is here's a weak acid that I'm starting with. This weak acid on my table 21 actually gives a certain pKa. So what is the pKa just for the sheer fact of being ethanoic acid or acetic acid? This pKa is actually equal to 4.76. And if you remember, we did a small derivation for our, let me just show it for you here. HA in the presence of water becomes H3O plus and A minus like this. Because we had said Ka is just going to be products over reactants, hydronium times A minus all over HA. If I had a buffer that had exactly the same amounts of A minus and HA, those would have canceled out. We end up getting pKa is actually telling me the buffer's pH right now. So right now, if I had equal amounts, I don't know exactly like, oh, well, they actually give you the concentration. The concentrated acetic acid is 0.100 molar. If the acetate was also 0.100, I would know that the pH right away is equivalent to pKa because those terms would have died away. Right? This time I need to have that whole Henderson-Hasselbalch equation because there is a little bit of a correction term. The equilibrium has shifted a little bit away from 4.76. First thing, 4.76 to 5 is not a big difference, so that's why it sort of still reminds me that it's in the buffer region, but we're going to need that Henderson-Hasselbalch equation. It is on your data booklet, so I can just look up section 2 here. The Henderson-Hasselbalch equation is given. If you want to find the pH of a buffer system, it's basically equal to pKa, but there is a correction term by log. Depending on the ratio of the conjugate amounts that we have, that's actually going to be a slight correction term. So let's see if we can put this all together then. So the pH I want is 5.00. The pKa at first was going to be 4.76. I want to know what conjugate base amount, how much acetate should I actually have? That's going to be an X right now. How much conjugate base should I have, given that my conjugate acid is currently 0.100 to make this true? So let's try it here. 5 minus 4.76. So this gives me here 0.24 is equal to the logarithm of this quotient here. I'm going to undo the log by anti-logging it. So 10 to the power of 0.24. Careful, it's not anti-log negative this time, so it's just anti-log 0.24. This gives me here the concentration A minus divided by 0.1. And just let me clean this up a little bit here. The concentration A minus anti-log of 0.24 do the multiply by 0.1 gives me a concentration of 0.174 molar. Right? So essentially, for a buffer, we had expected the pH to basically be the pKa if the concentrations were equal. We've actually shifted the equilibrium a little bit. Right now here it's in the slightly more basic than it should be. So therefore, what's happened here is we've added base to kill off some of the H+. We caused the equilibrium shift to the right, and now we actually found that the acetate concentration actually needs to be some 0.174 molar for the ratio of the conjugates to end up giving you this correction term. Now the pH would actually be 5. At this point here, we're basically done. The acetate concentration needs to be 0.174. The acetate came from sodium acetate. I can show you the step here. NaCH3COO. It's a one-way arrow to become Na plus and CH3COO. This is similar to that hydrolysis here. For hydrolysis, we're not worried about the salt itself. Water would have actually separated positive from negative. There was no reason for this one here to hydrolyze, but in this case here, I know sodium is a group 1 salt, so that one's there as a spectator. It's actually this acetate here that actually as a conjugate acid, it participates, it actually reacts with water to generate a little bit of hydroxide, knocking the pH a little bit higher. In this question here, we're just going to look at the numbers. So I have 0.174 molar of acetate. That must have come from 0.174 molar of your salt. And now we're ready to find grams. Reminds me I do need to use molar mass to get to grams. So now I know my volume was just a 1 liter. The concentration is supposed to be 0.174. Let's go 1 liter times it by 0.174 moles for a given liter. We're going to multiply it by the molar mass, 82.04 grams for a given mole. And this one here gives me 14.3 grams. Okay. So this was our sort of first way of making our buffer system. You're basically arbitrarily coming in, adding the conjugate. Once I have appreciable amounts of both, from the perfect sort of starting point, 4.76, we have shifted the equilibrium over a little bit, but still I have good appreciable amounts of both. It is still a buffer system. All right. In today's lesson here, we're going to just rehash over a little bit with what we know with titrations. This one here, if you remember, titrations are a really common chemical technique. Titration is a process where a measured amount, usually dropped from a burette, measured amount of solution is reacted with a known volume of unknown concentration solution. So it's a reaction between two solutions until a very special name here, until a desired, we're going to use this term here, equivalence point. Equivalence point is reached. This equivalence point here is also referred to, so either call it equivalence point or also call it a stoichiometric point for the blank here. Basically, at this equivalence point or stoichiometric point, it's when you have perfectly added in the right amount. In this case, it is going to be an acid-base titration. So there's just the right acid, just the right base, that there's actually no excess left over. So no excess. It's exactly the stoichiometry required, so then I can end up doing my calculations. So if I have a generic equation here, let's say A to the A, BB, becomes CC and DD like this. If the mole ratio, say, wasn't 1 to 1, let's do the ratio between, let's say, what's A over B? What is that coefficient ratio here? And what we have is moles of the chemical A that I dropped in is actually going to match up with moles of chemical B. Right? Not necessarily equal, because the mole ratio is not necessarily always 1 to 1. Probably an easier way of saying that here, yes, even though the acid may be a little more complicated, base may be a little more complicated, the equivalence point or stoichiometric point is essentially when the moles of H plus equals the moles of base. You're actually using one of these particles to count how much unknown of the other one that we have. Right? We will revisit another vocabulary term very shortly. It's going to be called endpoint and transition point. Those ones have to do with the indicator. Of course, I would want to choose an indicator that tells me when I hit this equivalence point, but it's totally possible I may have done a titration. Whoops, my indicator changed color, nowhere close to this equivalence point. In that case, there it wouldn't be a good titration for me. Right? So let me just sketch out a typical titration setup here. So we have a burette. Usually our burettes are 50 ml burettes. Remember, the markings are sort of upside down. The zero's on top, the 50 ml is on bottom. Essentially, you're going to have one solution in the top. you're going to take a starting reading. This is volume initial. Let's say for argument's sake here, this one is 0.100 molar NaOH solution. You might refer to a solution where you know the concentration. You might refer to this one here as a standard solution. If it's not a standard solution, you might have to standardize for it to figure out the NaOH. And basically what I'm going to do is I'm going to slowly open and close the stopcock valve on the bottom until the indicator changes color. The indicator will hopefully change color where it should at the equivalence point, stoichiometric point. That's when I know that there's no excess. I'm going to take a V final reading. I'm going to do the subtraction to figure out how much volume I've actually added and basically use the hydroxide to actually count how much acid there is. So this is an acid-base neutralization. Maybe it's between NaOH and HCl. I'm going to keep the mole ratio just 1:1 for now. This one here does actually end up forming table salt. Right now, our goal of a titration is to find, at this equivalence point, I want to know the concentration of my HCl. I want to know the unknown amount of acid. This one here could have a lot of H+, it could have very few H+. What I'm doing is I'm dropping in the OH- slow enough to actually count how much H+ there is. So what's going to happen here is you drop in OH-, as long as the OH- can find an H+, it neutralizes, it cancels out. I'm looking for the equivalence point when I've perfectly dropped in the right amount of base that counts the number of acid. Well, I don't know how much acid is there. Well, I do this technique here to actually control, well, how much volume do I need to drop in until this point happens. If it's really concentrated, I need to drop in a ton of volume. If it's not very concentrated, I don't need to drop in as much. But basically, we're going to hit this equivalence point so that when you drop in that last drop of hydroxide, it really can't find any other H+. That's usually when, if I chose the indicator correctly, the indicator's endpoint also changes color. That tells me to stop. I don't want to overdo it or else I have excess. As long as I have no excess here, I can basically start doing stoichiometric calculations. Okay. So that's just some of the terminology here. All that sort of background here, it sort of boils down here. Titration problems always have three parts to this calculation. What we're going to do, for one chemical, we will know the volume and the concentration. In this question here, I have, let's say, 0.100 molar NaOH. I'll be able to read a difference in volume. This is how much that you needed to actually hit an equivalence point. So let's make up that number here, 12.34 milliliters, right? The acid, I actually don't know the concentration. This is actually a question mark molar here. But we do, it's totally up to us how much of an aliquot, how much of a sample do I want to test at this point. Most of our pipettes are either 10 mils or 25 mils. So I'm just going to use a 10 mil pipette. At the end of the day, it is a stoichiometry problem. Because we have just hit the equivalence point, because we have no excess, I have just added in the right amount of base to kill off the acid. At equivalence point, these reactants are completely gone. So titration questions, start off with a chemical that you know more. I want you to calculate the moles of base, or acid, depending on the question. Calculate the moles of base by multiplying. So we have C is equal to N over V. You can find N by going C times V, multiplying the concentration and volume, right? So basically, you take this, find moles. Well, why do I want moles? Well, I just used the NaOH to count how much HCl there was. This is going to be in a mole ratio, not always going to be 1:1, right? That comes from the balanced equation. Basically, you're going to use your mole ratio to skip over. Use mole ratio to find your moles of acid, or whatever your unknown is. And then once you know that information, I've done this sort of painstaking task here. I now know how much HCl there is. I'm going to then use the last numbers. Most times they're going to ask you, well, what's the concentration? Well, concentration has to be moles per liter. What you're going to do is you're going to calculate the initial concentration, the starting concentration. Why did I make this note here? It has to be initial. I started off with just 10 milliliters of acid. That's all that the H+ was initially swimming in. I've just added in an extra 12.34. The total volume is now like 23, 24 or so. I don't want the diluted concentration. I don't want this number H+ now in my 24 milliliters. I knew that the H+ was actually only starting in 10 milliliters. So find the initial concentration by dividing the initial volume. The starting volume. How much you ended up pipetting. And that actually explains why sometimes with the titration, the whole point is being really precise. Sometimes you may get a half drop forming on this burette here, you can use water, you can squirt down any extra water, you can wash down the sides here. That may seemingly dilute the container. That's totally true. Well, I'm sort of wasting this solution here. I'm just needing it to count the H+. It's sort of unfortunate that I'm diluting it. But once I find the concentration, because concentration is intensive, the bottle where I took this H+ from, the concentration that I just found is going to apply to the entire bottle itself. Okay. Pay attention to your sig figs here. So the whole point of doing this titration is to be as precise as you can. I might even roughly give you what the concentration is supposed to be. You can still do a titration, do this mole ratio to actually figure out to more significant figures. In general, we try to have 3 or 4 sig figs here. Sometimes what we can do, because I don't necessarily know how much to hit equivalence here, usually this is referred to as a titrant. The titrant is how much I drop in. Usually I want my titrant to be at least 10 milliliters. Because what's going to happen here is your burette allows you to read 2 decimal places. If I only needed to add, let's say, 5 milliliters, I would at maximum have 3 sig figs, like 5.23, something like that. If my titrant is at least 10 milliliters worth of how much I'm dropping in, at least some number like 12.34, something like that, at least that's 4 sig figs. That's the whole point of actually getting to be really precise. Okay. So they're going to give us some sample numbers here. They tell us an equivalence point is reached by reacting this volume NaOH with H2SO4. Sure, they changed up the mole ratio on you here. Because this is an equation, let's do a balanced equation first. H2SO4 will react with 2 NaOH. This is going to end up becoming Na2SO4 and becoming 2 waters. You can remember the net ionic equation was the acid produces H+, the base produces OH-. These react in a 1-to-1 ratio. So since sulfuric acid always has 2, I know right away I'm going to need 2 of the sodium hydroxide. And that's going to form 2 waters, and this one here should be balanced. For all titration questions, if you lay it out this way here, you should find that one chemical. I know the volume. This was dropped from the burette. This is my titrant volume. Great, it's bigger than 10. The concentration of this one here is already really well standardized. I already knew this concentration to a really good precision. What I want to know is, in my pipette, I decide to test an unknown amount, unknown concentration, but the amount was 25 milliliters. Okay, so you take the chemical that you know more. Let's find moles. Once you find moles, you can use your mole ratio. This time it is 2 to 1. And then moles and that milliliters, I can divide those two to end up getting concentration. Sometimes they actually give you the concentration. They figure out what volume do we need for the titration to occur. We can still do it with that last calculation there. So at the end of the day, it boils down to a stoichiometry problem. In a typical like sort of short answer problem, they may even separate part A, B, C. From their standpoint, they're trying to figure out where people are having trouble. From your standpoint, you could be like, oh, I didn't know how to do the question. Oh, let's do A first. A will probably be like, well, how many moles of base? What's B? Well, how many moles of acid? And then what's C? What's the concentration? I'm just going to do this all in one step here, so that way I don't accumulate any rounding errors here. Start off with the chemical that I know more. For all solution problems here, we're given a volume and a concentration. I always start off with the volume, albeit I need it in liters. So 0.02310. I don't start off with the concentration because concentration hides a mole per decimeter cube. That actually is a conversion factor. So 0.2055 moles for a given liter. That's going to tell me how many acid particles that how many base particles that I dropped in from the burette. To get to the acid particles, I use the mole ratio. For every 2 parts NaOH, it actually reacts just 1 part H2SO4. Equivalence point is still the base number has killed the acid number. It's just that the mole ratio was slightly uneven. At this point here, all our other units have died away. We end up with moles of acid. This part here is a little bit weird. We're used to going top unit cancels bottom, top unit cancels bottom, so on and so forth. In this case, I actually do want to have moles on top. I just need to pick up the initial volume in the bottom. Well, initially, it was actually in 25 milliliters. So all I'm going to do is I'm going to divide by 0.02500. That's 25 milliliters. That's the starting volume, and I just put a 1 on top. Okay? So I'm just going to punch this in here. 0.0231 times 0.2055, divide 2, divide 0.025. And this one here gives me the unknown concentration is going to be 0.0949. Okay. Paying attention to sig phase, 4 sig phase, 4 sig phase. How precise are these numbers? Well, these numbers here were actually in the recipe, so I'm infinitely confident those are exact. So I can actually have one more sig fig here, 0.9494 as the concentration. So sig figs do matter. I have now standardized H2SO4. I've used, this part here was totally from my burette, right? So figure out how much base I need to toss in until I hit this equivalence. I've now used it, and I've now found the unknown concentration. The H2SO4 is now a standard solution, and now I can use this to standardize other bases as well. But you notice that in a titration, you always need to make sure you already know one of the concentrations. So let me just make a side note here. So we just did a titration setup. We started off with the concentration NaOH. I knew the molarity was 0.2055. I knew from the titrant volume how much I dropped in. I dropped in 23.10 milliliters. I needed to know this concentration, and through this calculation, I ended up finding the acid that I was testing actually has a molarity of 0.09494. Again, just some terminology here. We have used the NaOH to standardize, to make that a standard, to standardize H2SO4. I've been able to figure out the H2SO4 because I knew the concentration NaOH. Now that this is standardized, I can use this to titrate other bases as well. My question, however, is, well, how did I know this concentration? Well, since this is a base, I could use an acid to standardize it. But then we get into this sort of chicken and egg question here. How do I find the starting concentration so that if I know the molarity, I can use this to standardize other solutions? Fortunately for us, we can actually calculate concentration another way. We can calculate concentration by moles per volume. It's just that I'm actually limited to a certain number of chemicals. NaOH turns out not to be a really good starting ingredient. NaOH actually comes to us in the form of pellets. NaOH here, you may be able to weigh out, let's say this is on a scale, you may be able to weigh out 1 gram. But the problem with NaOH is if you just leave it out open to the environment, water is going to very quickly absorb into these pellets here. It may actually start reacting with carbon dioxide in the air here. You may be using the calculation. Yeah, I dissolved 1 gram. I dissolved it into a solution of 100 milliliters. Well, because the NaOH here was really impure to start off, the concentration here won't be precisely 4 sig figs. What we actually want to do, this is just like a practical aspect of titration here. What we actually want to do is we actually want to start off with something called a primary standard. Right? Primary meaning it's the first. A primary standard is a solid that remains pure. Okay? And how do we know it remains pure? It does not react with water in the air, carbon dioxide, or other chemicals. So that if I have a really pure compound, baking soda, actually sodium carbonate here, this one here actually turns out to be a good primary standard because this compound here is so pure. When I actually put, let's say, 1 gram of sodium carbonate on this scale here, I'm pretty confident that the entire grams is actually sodium carbonate, not mostly sodium carbonate and some extra other gunk in there. Okay, so that if this one here is a primary standard, if I do the dissolving accurately enough, I use a volumetric flask and all here, I would know the concentration really well. Once I know one concentration, I can then use it to titrate a whole bunch of other samples. Na2CO3 is known as a basic standard because this is going to form a basic solution. We have an acidic standard we're going to use in our lab, KHP. I'll try to do a virtual lab at least for this. This is an acidic standard. Basically, there are only a few chemicals that are pure enough that could be a good starting ingredient. Once you have taken an acid, done a titration, and standardized NaOH, I had said NaOH was a poor starting product, but if I have found this number from another standard, if I now know this concentration really, really well, this one here can definitely be used to titrate other solutions as well. So the real problem is just what is your first starting standard. Okay. One other sort of practical note here, unfortunately when I do this, it is basically between H2SO4 and NaOH. Both of these are actually colorless solutions. What we're going to do is we're going to add in an indicator. The indicator is essentially an organic acid or base, and it changes color depending on acid or base. If I have added in that OH minus and it can't actually end up finding any H plus around, our indicator we've been using was phenolphthalein. It would turn to that pink color. I'm looking for the first hint to that pink color to tell me when the reaction is over. If it goes overly pink, you remember, oh, I needed to start over again. Or if you forgot to put indicator, another common problem. We will take a look at indicators a little more detail in the upcoming lessons here. What I want to show you is another way of actually tracking your data. What if I didn't have an indicator? would I still be able to figure out what the equivalence point is, what the starting concentration is actually? So how we're going to just change it up here. We're going to perform the same titration. We're going to start off with solution in the burette here, and what's going to happen here is we're going to slowly drop an NaOH. So again, base in the burette, I can drop the base. I'm going to drop it into this acid here, and what I'm going to do here is instead of actually using an indicator, I'm going to stick a pH probe here. And what I'm going to do is I'm going to sample the pH at any given time. Now, for starters, you might be like, well, if I already know the pH probe here, I already know the concentration. That is true, okay? But just to verify, sometimes pH probes aren't really well calibrated here. Let's just do it via what's referred to as a titration curve, okay? So what I'm going to do for you here, when you take a second, they're actually going to plot this as a titration curve. We've seen a sketch of this a couple times now. We're going to plot pH on the vertical axis. And because I'm slowly adding in NaOH, I'm going to plot this on the horizontal axis. And basically all that's going on here, before you add in any base here, the concentration of H plus happens to be 1 molar, the pH happens to be 0. I'm just tracking the pH, okay? So when I add no base, the pH happens to be 0. Okay, great. It goes through 0, 0. Then I'm just going to plot through these points here. At 0.25 is 0.22. So 0.25, 0.22. At 0.5 is 0.48. 0.5, 0.48. 0.75, 0.85, 0.75, 0.85, 0.9, 1.28, 0.9, 1.28, 0.99, 2.3, 0.99, 2.3. I'm starting to see that the pH is actually steadily increasing here. 0.99, 3.3, so just a little bit over here. It's now 3.3, 0.9999, 4.30. Oh, I'm seeing that the pH is actually shooting up pretty quickly here. When I hit 1, we're at a pH of 7, okay? Then 1.001, I'm already at a pH of 9.70. This is an experimental sort of finding here. So 9.70. 1.001, just a little bit over, I'm already at 10.7. So a little over there. 1.01, 11.7. 1.01, so 11.7, something like that. 1.1, 12.68, 1.1, 12.68, 1.25, 13.05, 13. Do this graph for yourself. 1.75 is 13.44. 1.5 is 13.3. Sorry, 1.75 is 13.44. 1.75 is 13.44, maybe somewhere out there. And then 2, the final reading, when I've added 2 liters worth of base, is actually 13.52. Okay. Remember, I have not tossed in any indicator this time. I'm just sampling, drop in a little bit of base, track the pH. Drop in more, track the pH, track the pH. I'm just tracking the relative change in pH as this occurs. Obviously, I just took readings at very particular intervals. I took readings where more interesting things were happening. So I took a lot of readings here close to 1 liter. That seems to be the special point for this mixture. But being a graph here, we can actually just follow the trend here. Let's do a best fit line here. This graph here steadily increases, it suddenly shoots upwards, and then suddenly goes up this way. Okay, so let's just make some general observations here. Does it make sense that this pH is increasing? Well, for sure. I am adding a strong base, right? I would expect it to slowly go higher and higher. We can assume we're at 25 degrees, so pH 7 should be neutral. It seems like that pH 7 is actually a special point for this titration. So the pH, this is neutral at 25 degrees, okay? Remember that this is on a logarithmic scale, so every step is sort of 10 times harder than the one before it. So that's part of the reason why, yeah, I may be actually neutralizing a lot of base, but it's not actually jumping all that quickly here. But as I get close to what we're going to later on call the equivalence point here, well, these ones here are a lot closer to neutral. These steps here are a lot smaller than trying to get so far away. So that's part of the reason why this one here is so sudden, such a steep jump like this. Let's take a look at why there's this steep jump. We started off here with a mixture. We had a bunch of H+. It's a strong acid. Slowly what I've done is I've added in OH- into the container. I'm going to draw a picture here. Let's say I've been killing off the H pluses, right? So I drop in an OH minus, it kills off an H plus, it becomes a little bit more basic. I drop in a little bit of OH minus, it kills the next H plus, no problem. When I drop in the very last drop of H plus at equivalence point, notice that the base has perfectly killed off the acid. That would imply to me I would expect the equivalence point supposed to be pH 7. This is my special point. This is when our moles of base that I added is perfectly matched up to moles of acid. Okay, I'm dealing in this situation with a strong acid, strong base equilibrium a reaction. So HCl reacts with NaOH. At equivalence point, I have perfectly added the right amount of base to kill off the HCl. Let's make sure that the salt doesn't accidentally hydrolyze on us here. We get just plain old table salt and water. Water definitely is neutral. If I try to do a hydrolysis of table salt here, I dissociate NaCl to form Na plus and Cl minus. Phew. Na plus is a group 1 salt. That one is a spectator. It doesn't react with water. Cl minus is the conjugate of HCl, strong acid. This one has no chance of going backwards because there's no hydrolysis. There's no extra H plus or extra OH minus ions of form. The pH exactly 7. So there's our conclusion here. The pH is exactly 7 at equivalence. We're going to do titration curves just roughly for a weak acid and a weak base later on. We're going to see that because of hydrolysis, that pH here might not be the same as well. All right? So that's one important reading here. It won't always be 1 liter. That one there was just for convenience here. But there is going to be this sort of shooting up point. Basically, I've dropped in the hydroxide. It killed off the last acid particle, so the very last acidic pH. Then I get a pH of 7. And then when I drop in one more drop of hydroxide, this OH minus can no longer find any acid particles to neutralize. Well, since it's OH minus, it's going to be basic, I'm going to suddenly have jumped up within a really narrow band. I'm going to have jumped up to this higher region here. So within, this is sort of that one last H plus that I had. This is when we had nothing left over. This is when we had 1 particle OH minus. That all happens within a very, very narrow range of pH. This volume here is given a very special name. We're going to call this VB. So this is the volume to reach equivalence. Again, it's not always going to be 1 liter. That was just for convenience for you here. But if I plot out a titration curve, you should be able to identify for me VB. In tomorrow's lesson, we're going to do more of these calculations. We're going to actually take half of VB. We're going to go, well, if that's 1 liter, that's when all the special things are occurring. Well, half of it is 0.5. This is going to be called V half. And then we're going to track down, not so important for this graph here, we're going to call this a pH half, the pH at which the volume is halfway to the equivalence, and we'll also need the pH initial. So at least plot that graph here for yourself here. If I actually had phenolphthalein, phenolphthalein actually changes color roughly between 8 and 10. So this is a sort of nice foreshadow here. So phenolphthalein, we actually have a table later on to actually specify between, I think it's 8.2 to 10.0, that's when phenolphthalein changes from colorless to pink, right? Uh-oh, I was looking for the equivalence point. I was looking for the pH 7 point. That's the point to stop. If I actually have a pH of like 8 or 9, I've actually overdone it. I'm a little bit over. But what you're seeing on the titration curve, because within a very, very narrow range of volume that you added, this shooting up happens really, really quickly. As I blow through the pH 7, I'll probably have blown through pH 9, pH 8, or whatever, and that's when my phenolphthalein would have changed color. That's when my solution would just look pink overall. I still take down a few readings so I can get the rest of that shape of that curve, but at least where it suddenly jumps here is near the equivalence point. That's when the moles of base has killed off moles of acid. Okay. So see if you can answer your way through some of those questions. I'm just going to roughly show you a few graphs. We'll do the calculations in more detail tomorrow. This is the graph that I showed you, HCl, NaOH. The pH is perfectly 7 at equivalence. What if we have let's do a weak acid, strong base titration here. So we had alluded to this. So acetic acid and sodium hydroxide. This is going to become sodium acetate and water. Same thing's going to happen. My titrate or my titrant, I'm adding in base. I'm adding in hydroxide. I would expect the OH minus to increase. Notice that this one here is currently, it's a weak acid. So in comparison to the strong acid curve here, a weak acid here if I'm playing fair with molarity here, starts higher as a pH. It isn't that good at ionizing to actually knock us into the really low pH 0, pH 1 range. So I start a little bit higher. There is going to be this sort of shooting up region here where I have that one last drop of H plus acidic. I have it completely at equivalence. That's going to be the middle of this jumping up region. And I have the drop of hydroxide. It can't find any more acid. Now we're suddenly basic. This part here is definitely going to be the equivalence point, no problem. But what you're seeing is for a weak acid strong base curve, the equivalence point, pH is actually bigger than 7 at equivalence. But I thought equivalence was supposed to be the perfect stoichiometric point. All the reactants have killed themselves off. That's true. The weak acid has killed the NaOH. This should be pH 7. But we've seen a couple times now, well, NaCH3COO, this is a salt that can hydrolyze. The Na is a spectator, the Chukwu. This Chukwu here actually acts as a weak base. This one here will actually reform a little bit of conjugate acid, but in doing so, it ends up generating a little bit of hydroxide. So even though we're at equivalence, we're slightly in the basic side. One easy way to just sort of remember that, if I have a strong acid, strong base, nobody wins. The pH is 7 at equivalence. If I have a weak acid, like this Chukwu, weak acid and strong base, the base sort of wins out, so the pH is big in this. What if we just flip that logic around here? What if we have a strong acid and a weak base curve? So I start off with a strong acid, I start off with a pH really, really low. We'll talk about why there's a buffer region more in tomorrow's lesson. But we have a strong acid, weak base here. Let's do the reaction between these ones. HCl reacts with NH3. This is going to end up forming NH4+, right? As the acid, its job is to donate the football over. NH4+, we're going to get Cl-, right? So we can just say NH4Cl. We're always going to be neutralizing to form water, right? The ammonia somewhere along the way is going to generate hydroxide for you. At equivalence point, these guys have killed themselves off, right? It's stoichiometric, right? All the moles have, I perfectly counted it. But NH4Cl is such that it becomes NH4+ and Cl-. Cl- here is the spectator. This one here can't hydrolyze. So actually the NH4+ reacts with water. Well, this is cationic hydrolysis. It's going to be able to, a certain extent, toss the football back over, reform some weak base, and in doing so, generate some acid. Not a lot, right? But enough that even at equivalence, when this point here jumps up, for this point here, the equivalence point, right? Basically, we have no reactants left over. The pH is actually slightly less than 7, slightly acidic. And again, you can make a note to yourself here. If I have a strong acid and a weak base curve, the acid wins out and it pushes the equivalence point. It pushes this center point, this special point, when everything is cancelled out, slightly into the acidic region. So tomorrow we're going to have a look more so at these titration curves. We're going to do this a little more detail with them calculations. Rarely we're going to deal with weak acids and weak bases. The problem is if both of them are weak, both of them are going to be equilibria. And in that situation here, although you will have a sort of jumping up point here, it won't be as obvious, and let alone the buffers won't be as obvious as well. As we do eventually get our way to indicators, you do want to choose an indicator that is roughly at the right pH. If I'm expecting the pH 7, I want an indicator that changes about 7. If I'm expecting the pH is going to be slightly higher than 7 at equivalence when I want to stop, I might choose phenolphthalein because that changed as 8.2 to 10. If I know that the pH is going to be somewhat less than 7, right, that's when it actually changes. I probably don't want to use phenolphthalein. The color change occurs a little bit too late. I'm going to check my table for another indicator that changes color earlier. Okay, so more on this in tomorrow's lesson. Thanks, guys.